All right, so today I want to talk about two topics. The first topic is limits at infinity, which is related to horizontal asymptotes. So the first would be limits at infinity. So we want to study the behavior of functions, some functions, when x approaches infinity. That means when x becomes a very large number. One of the most important examples is this one. So f of x is 1 over x. And I can draw the graph of this function. So the graph looks like this. We know that when x goes to 0, this function goes to infinity. And when x goes to infinity, the function goes to 0. So this is y equal to 1 over x. Now, when x goes to positive infinity, whether x goes to positive infinity or the negative infinity, the limit would be 0. So here is the positive infinity limit. So I'm just writing limit of 1 over x. X goes to positive infinity is 0. And on the other side, when x goes to negative infinity, you see that again the limit of 1 over x, x goes to negative infinity is again 0. So, and whenever you have a function whose limit at infinity is a number like 0, 1, 2, 3, then that function has a horizontal asymptote. So for example, here, y equal to 0 is a horizontal asymptote for f of x, 1 over x, because the limit of 1 over x when x goes to infinity is 0. Okay. So another important example is f of x equal to e to the power x. So I can draw the graph of this function. So this is the graph. So y over is equal to e to the power x. Again, you see here when x goes to minus infinity, the limit is 0. So I'm writing here, limit of e to the x, x goes to minus infinity is 0. Why it is 0? Because e to the minus infinity, and the reason is e to the minus infinity is equal to 1 over e to the power infinity, which is 1 over infinity, which is 0. So in the previous example, we saw that 1 over infinity is 0. And here you have e to the power minus infinity, which is 1 over e to the power infinity. E to the power infinity is again infinity. imagine a very large number, like 100. E to the power 100 is a very, very large number. I mean, even bigger than 100, of course. So again, you have 1 over infinity, which is 0. So again, here we say that y equal to 0 is a horizontal asymptote for f of x equal to e to the x. So in general, if you have any function in general for function f of x, if the limit of f of x, x goes to either positive or minus infinity, I mean, either of them is equal to L, or maybe just let me separate them, because even one is enough. If either the limit of f of x, x goes to positive infinity, or the limit of f of x, x goes to negative infinity, is equal to L, then we say that y equal to L is a horizontal asymptote. And I can show you just a simple picture. So in general, you have a function. Let me draw a simple picture. You have a function. Imagine that this is a function. And the limit at infinity, for example, is some number L. This is y equal to L. So you see here, when x goes to infinity, f of x becomes closer and closer to L. So here we know that limit of f of x, this is y equal to f of x. So limit of f of x, x goes to plus infinity is L in this picture. So we say that y equal to L. So y equal to L is a horizontal asymptote. Let me tell you more examples. So sometimes, for example, we have rational functions. So another example. So example of rational functions. For example, a function f of x equal to 3x minus 1 over x plus 2. So we want to find if the limit at infinity exists or not. So the limit of f of x, x goes to infinity. This is equal to limit of 3x minus 1 over x plus 2, x goes to infinity. So the best thing for rational function to do when you compute the infinity, limit and infinity, is to factor out the highest or the top degree term. For example, on the top you have x, so you can factor out x. So that means on the top you have limit of x times 3 minus 1 over x. And the highest term, I mean the top term at the bottom is also x times 1 plus 2 over x. X goes to infinity. Now, when x, first of all, here, what we can do is we can cancel out x with x. So they cancel out each other. Second of all, so 1 over x, when x goes to infinity, is 0. When x goes to infinity, this guy is 0. This guy is also 0. So at the end, we have a 3 on the top and 1 at the bottom. So this limit is equal to 3 over 1, which is equal to 3. So that means that this function has a horizontal asymptote that is y equal to 3. So y equal to 3 is a horizontal asymptote. I mean, it's good to draw the graph of this also. So what is the function? We have f of x equal to 3x minus 1 over x plus 2. And we know from before that x equal to 2. So we know that x equal to 2 is a vertical asymptote. Because the limit of this function when x approaches to 2 is infinity. And we just observed that y equal to 3 is a horizontal asymptote. Now we can draw the graph. So let me just first draw y equal to 3 and x equal to 2. So y equal to 3 is like this. Let me just draw the line. This is y equal to 3. And x equal to 2. This is x equal to 2. Now you can draw the graph. Let me use another color. So I use green. So this function at 0, when x equal to 0, is -1/2. So at 0 is -1/2. Like, so it crosses this point. And when x equal to 1/3, it will be 0. So x equal to 1/3. Like here. Now, if I want to draw the graph, so that means, let me just check, x equal to 0, you have -1/2. Oh, sorry, x equal to -2 is a vertical asymptote. So I don't know why I put 2. So I have to correct myself. X equal to -2 is a vertical asymptote. Because when x approaches -2, this guy goes to infinity. So I have to erase this guy. So you have x equal to -2. Okay, now I can draw the graph. It's like this. So this is the graph of y equal to 3x minus 1 over x plus 2. So this is the horizontal asymptote. You see the horizontal asymptote behavior here, and you have also the vertical asymptote here. Okay, is that clear? Is the graph clear? So as an exercise, I want you to draw. This is an exercise for you. So draw the graph of draw the graph of each of these functions and indicates the horizontal and vertical asymptotes. So the functions are f of x equal to 2 minus 1 over x, then b, f of x is 1 minus 2x over 3x plus 1, and c, f of x equal to x plus 1 over x minus 1. So draw the graph of each of them and indicates the horizontal and vertical asymptotes. Okay, and let me give you also, this is the last example. Sometimes we have some rational functions which can be more complicated. So for example, look at this function, f of x equal to x cubed plus 3x squared plus x minus 5 over x to the power 4 minus 2x plus 1. And we want to find the limit at infinity. So the limit when x goes to infinity of this guy, x cubed plus 3x squared plus x minus 5 over x to the 4 minus 2x plus 1. So as I said, for the rational function, the best thing to do is to factor out the top term on the denominator and numerator when we want to compute the limit at infinity. So on the top, you can factor out x cubed. So it would be x cubed times 1 plus 3 over x plus 1 over x squared minus 5 over x cubed at the denominator. If you factor out x to the power 4, you get 1 minus 2 over x cubed plus 1 over x to the 4. And x goes to infinity. Okay, now you can simplify x cubed with x to the 4. So you get x at the bottom. Moreover, you have to note that 3 over x when x goes to infinity is 0. 1 over x squared is also 0 when x goes to infinity, because 1 over infinity is 0. This is something we always keep in mind. 1 over infinity is 0. It doesn't matter, positive infinity and negative infinity, both 0. This is also 0. This is also 0. This is also 0. So at the top, you get 1. And at the bottom, you have x. And x goes to infinity, which is again 0. Okay, so as an exercise, just following this logic, I want you to compute this limit a is limit of x goes to infinity of x squared minus 2x plus 1, and the bottom you have x squared, 2x squared plus 2x plus 3. B, again, limit x goes to infinity, 1 minus x cubed. So this is x cubed. At the bottom, you have 4x cubed plus x squared plus 3. And the last one, limit x goes to infinity of x to the 2x to the power 4 plus 3x cubed plus 2 over one minus x to the power 4. Okay, compute each of these limits at infinity, and remember that if you have a function whose limit at infinity is a number, is a finite number, like 1, 2, 0, anything, any finite number, then that number is a horizontal asymptote for the function. So y equal to that limit, a finite limit, is a horizontal asymptote. Do you have any questions so far? You hear me?
Yeah, I can hear you. I don't have any questions.
Okay, great. So I want to move on to another topic, which is basically the beginning of derivatives. So I want to go to basically to the next chapter, the next unit, which is derivatives or differentiation. Derivatives. What is the definition of a derivative? So derivative, which is also known as instantaneous rate of change, so also known as ARCA, instantaneous rate of change. So what is the definition? Or what is basically this concept means? So first of all, what is the rate of change? If you have a function like y equal to f of x, so rate of change means, so we look at x equal to a. So for x equal to a, the value of the function is, so y equal to f of a. Now imagine that there is a change in x. So now x, so x1 is a, x2 is a plus h. So there is a change in x. So then y would be f of a plus h. So maybe I call it y1 and y2. So the rate of change for this function in this interval from a to a plus h is basically equal to the change in y. I call it delta y. So delta y is the change in y. I mean, means the change in y over delta x. So delta x is the change in x variable. So what is the change in y? So it's y2 minus y1 over x2 minus x1. But since we know y1 and y2, we just can plug in the values. So this is f of a plus h minus f of a over, now what is delta x? x2 minus x1 is just h. So this fraction or this quotient is called the rate of change of this function f at this interval from a to a plus h. So if I can just draw some simple picture so you can see what's going on. So you have a function y equal to f of x, and you have f of, imagine this is f of a, this is the point x equal to a, and this is f of a plus h. So if you look at this triangle, this side is delta y, this side is delta x. So as we defined, basically the rate of change is delta y over delta x, which is basically the slope of this line. So a slope of, this is the slope of this line. The line that goes from a and f of a to a plus h and f of a plus h. Now, what is the instantaneous rate of change? Instantaneous rate of change, when this interval, the x interval, goes to 0, that means this interval becomes smaller and smaller, then we have the instantaneous rate of change. So instantaneous rate of change, let me write it. So the instantaneous, I'm writing it here. Instantaneous rate of change is equal to the limit of f of a plus h minus f of a over h when h goes to 0. So this ratio is the instant, or this limit is the instantaneous rate of change of the function f at x equal to a. So instantaneous rate of change, maybe I just write at x equal to a. Or you can simply imagine this as the limit of, maybe I'll write it by red. So this basically is the limit of delta y over delta x when delta x goes to 0. For example, Consider this function. Imagine that the f of x is x squared plus 1. So we want to find the instantaneous rate of change when x, so the question is compute the instantaneous rate of change, or sometimes briefly we can just say IROC. So IROC stands for instantaneous rate of change. So compute the instantaneous rate of change at x equal to 2. So remember the definition. So instantaneous rate of change is equal to the limit of f of 2 plus h minus f of 2 over h when h goes to 0. So now, what is f of 2 plus h? F of 2 plus h, so I just have to plug in. So this would be the limit of f of 2 plus h is 2 plus h squared plus 1 minus f of 2. F of 2 is 2 squared plus 1 is 5 over h goes to 0. So this would be equal to the limit. So on the top you have 2 plus h squared plus 1. 2 plus h squared would be h squared plus 2h plus 1. And you have, sorry, plus 4, that's plus 1. Oh, sorry. 2 plus h squared is h squared plus 4h plus 4. This is 2 plus h squared. And then you have another one, minus 5 over h. H goes to 0. So 4 plus 1 is 5, and then you have minus 5, so they're gone. So you have on the top the limit of h squared plus 4h. Now if you factor out h, you get h times h plus 4 over h. H goes to 0. So h times h plus 4 over h. Now you can cross out h with h. So you get limit of h plus 4 when h goes to 0. This would be 4. So that means the instantaneous rate of change at x equal to 2 is 4. Okay, now I just have some remarks. So the first remark is, so we also call this quotient or this limit, this is also called the derivative of the function f. So this is called the derivative of f at x equal to a. So this is called derivative of f at x equal to a. And we write it as f prime of a. So when I say f prime means the derivative of f and at a. So instantaneous rate of change basically is equivalent to the derivative. And that is the definition of the derivative of the function f at x equal to a, and we write f prime of a. So this is f prime of a by definition. This is the first comment. The second comment is that this limit that you see here, this quotient, it's 0/0 limit. So this is an indeterminate limit always of the type 0/0. So you have to work on it in order to compute it. Okay. Okay. So that means so far we have learned that the derivative of f at a, that we can write as f prime of a, is defined to be this limit of f of a plus h minus f of a over h goes to 0. Now I give you some exercise. So to compute, so this is A, part A is f of x equal to the square root of 2x plus 1. So compute f prime at x equal to, for instance, 4. So compute f prime of 4, b, f of x is equal to 2x cubed plus x squared minus 4x plus 1. Compute f prime at f prime of 1. And c, f of x equal to x plus 1 over 2x plus 1. So compute f prime at 0. So remember, f prime of a is given by this limit. So for example, for part A, you have to compute the limit. So this f prime at 4 is equal to the limit of f of 4 plus h minus f of 4 over h goes to 0. Now you have to plug in the number into the function. So I pause for a little bit now. So first of all, this limit is indeterminate and of the form 0/0, right? This is 0/0 because when h goes to 0, so the denominator is obviously 0, but the numerator is also 0. Now for this, because you have a square root, you can multiply by its conjugate. So basically you can multiply the top and the bottom by Let me move it a little bit here. So you multiply the top and bottom by the square root of 2h plus 9 plus root 9. And you have to divide it by the same thing. So 2h plus 9 plus root 9. Okay. So once you multiply, so you remember a minus b times a plus b is a square minus b square. So you have on the top, you get 2h plus 9 minus 9. At the bottom, you get h times root 2h plus 9 plus root 9. So if you simplify, 2h plus 9 minus 9 is just 2h. And the bottom, you have, on the denominator, you have h times this guy, 2h plus 9 plus root 9. Now, because now, first of all, you can cross out h with h. And then when h goes to 0, so on the top you have 2. At the bottom, you have, because h goes to 0, 2h is just 0. So you have root 9. Root 9 is just 3. So you have 3 plus 3, 6. So that would be 2 over 6, which is equal to 1 over 3. Right?
Yeah.
Okay. Now let me go to the textbook. Do you see my computer, my screen? Sorry. Do you hear me? Sorry.
Yeah, I hear you.
Okay. So if you go to the textbook, chapter 3, 3.2. So the textbook on the website, chapter 3.2. I can even show you on the website. So this is the course website. So you go to the derivatives, chapter 3.2. Derivatives, chapter 3.2. And then you go to the exercises 3.2 on page 243. So please do number 54, 54, 56, 58, 62, and 63. So again, I repeat 54, please write it down. 54, 56, 58, 60, 62, and 63. And also next page, the next page, do 68, 70, 71, and 73. So 68, 70, 71, and 73. So try to do this, and I'm here. If you have any questions, you can ask me, okay?
Okay.